All right, so lesson 1 here. We want to start looking at limits by first of all getting an understand of what we're finding when we're asked to find a limit. We're also going to introduce the notation that we're using, and then how to use a graph, and also how to use some algebra in doing this. Okay, so first of all, just defining a limit. All right. A limit is the value that the dependent variable, which usually is y, approaches as the independent variable, often x, approaches some fixed value or infinity. Okay? So, what we have here is we have our independent variable x, and we want x to get really close to, we want it to approach a certain value. Okay, or we can have it approach infinity, go off to infinity, positive or negatively. And then what we're doing is we're saying, okay, if that independent variable, or we could say the input, is approaching a certain value, what is our dependent variable approaching, or what is our output getting really close to? Okay, and the key word in this entire definition that will really help you avoid confusion is this word approaches. Okay, if you can really remember that word as we're going through this, that word approaches is a critical word, because limits don't have to be confusing. But if you have the idea of equal instead of approaches, that's when you're going to get confused. All right, so keep in mind that idea of approaching. All right, now just a little bit of a preview here. The limit, I kind of view the limit as the foundation of all of calculus. Okay, when I learned calculus, I was kind of taught that there are 3 pillars of calculus: the limit, the derivative, and the integral. Okay? Personally, though, I think that rather than calling them 3 pillars, I believe that the limit is really the foundation. Because you actually use limits when you're developing the derivatives and your integrals. Okay? So I prefer to say that there's 2 pillars of calculus, and then the limit is the foundation of everything. All right? And then you have all the rest of calculus that's built on that. Okay? Now, we use this limit to find the slope at a point on a curve. That's the basic definition of what a derivative is. We also use it to find the area on a plane bounded by the graphs of different functions. That's the basic definition of what an integral is. Okay? So what we're learning right now is that foundation for both of these big ideas in calculus. Okay? So let's look at this before we even get into notation. Let's look at what we are talking about. Okay? So we can estimate a limit based on a graph. Okay? So if we're given some kind of a function, we can graph that function. And then what we're doing when we're estimating a limit is we're going to visually identify the y value as x is approaching c. Okay? Now c is just some number. All right? So let's say this function is our f of x. Okay? And what we're going to do is we're going to find the limit as x approaches c of f of x. Okay? Or you might read it the limit of f of x as x approaches c. You can say it either way there. The notation for this, we use the abbreviation LIM, and underneath that we put x approaching c. But that by itself means nothing, okay? It's kind of like just writing sine, all right? Well, sine of what, all right? Well, the limit has to take some kind of a function that we're finding the limit of. So we would say the limit of f of x as x is approaching c. Okay? So, depending on what that value of c is, will determine what the limit is approaching. Okay? So let's say c was right here. Alright, so you look at your graph and you identify, in this case, there's actually a point that the graph is going through when x equals c. So you can just look at the y coordinate, and that's going to be the y for that value of c. Okay? So we could say the limit as x approaches c of f of x is whatever that y value is. Okay? Now the interesting thing is we'll look at a lot more later on, is that the function doesn't have to actually hit that point in order for the limit to exist. And that all goes back to that word approaches. All right? The approaches idea. Okay? So that's one way that you can estimate a limit, just by looking at the graph and seeing what the y value is. And there's a lot of different things that come into play here that we'll look at as we move forward. Okay? A second way is a numerical method for estimating a limit. All right? And here we actually get a definition of when a limit actually exists. All right? We can use a table of values to identify the value that y is approaching as the numbers approach the given x value. All right? So you can create a table. All right? But here's the rule. Okay? Both limits as x approaches from the right and from the left must exist and must be equal, or the limit does not exist. All right? So here we have the concept of one-sided limits. All right? One-sided limits. So let me illustrate what we're talking about here. Okay? One-sided limits. All right? So, on the x-axis, the left side is the negative, right? And the right side is the positive. So we actually use some pretty intuitive notation here to give our left-sided and our right-sided limits. Okay? If we want the limit from the left, all right, here's the notation that we're going to use. Okay? We would take the limit of f of x as x approaches c, and then we put a little negative like that. Don't make it negative c, that's different. All right? But it's approaching c from the left. That's how you would read that. Okay? If we are coming from the right, what do you think the notation is for that? Yeah, we're going to do the same kind of thing but with a plus sign instead. Okay? So x is approaching c from the positive side, because the right-hand side of our x-axis is the positives, okay? So that's some basic notation. In order for a limit to actually exist, both of those have to exist and they have to be equal, all right? Now we'll revisit this idea later on to see how that plays out. But right now, as we're looking at a numerical approximation, what we have to do is we have to actually, we can use a table and see what the numbers are getting close to. And they should be getting close to each other because they have to be approaching the same value. Okay? We'll actually do an illustration of this in a moment here. Okay? Now, one quick note, and this is particularly the case when we have piecewise functions, which we use a lot here in AP Calc. The limit is independent of the actual y value. Okay? I'll illustrate that really quickly here. Let's say I have this function and there's a hole, and then it goes like this. Okay? And let's say this piecewise function has the actual point of the graph right there. Okay? The limit is not going to equal that y value, even though the function equals that y value. Okay? The limit will actually equal whatever this y value is, because from the left side it's getting close to that value, and from the right side it's getting close to that value, even though it doesn't actually equal that value. Alright, that's why, again, approaches is the key idea here. Okay? So, how do we solve a limit? Alright, we said you can look at the graph, we can estimate using the table. Both of those are kind of imperfect methods. So what's a general strategy for solving a limit? Okay, we always want to begin by trying to just plug the number in. Whatever that value of c is, try just plugging it in. If it works, and you can tell the function is continuous, then you know that that's what the limit is going to equal. Okay? Sometimes it doesn't work though. Sometimes you get a 0 in the denominator of a fraction, or you get 0 over 0, what we call the indeterminate form. You might get a negative in a radical or something like that. You've got to be able to work that out and see if we can't figure out what the limit is a different way. So we try to simplify, factor polynomials and reduce fractions to remove holes in our graph. Cancel things out. Try to rationalize. If we've got a radical function, we can try to rationalize. Later on, we'll revisit limits after we've done derivatives, because there's something called L'Hopital's rule that actually makes finding limits much easier if you have a 0 over 0. Okay? But then we can use both of these previous methods of estimation that we looked at. We can use our calculator really efficiently to do. Okay? How many of you have your calculators with you today? All right, you got it? Okay. Go ahead and get it out if you've got it. If not, I can show you what we're going to be doing here. All right. All right, so if we want to graph x cubed minus 1 over x minus 1, what do we have to remember if we're punching it into the calculator? Use the parentheses, okay? So parenthesis, clear that. Parenthesis, x to the third minus 1, close your parentheses, divided by x minus 1, parentheses, x minus 1. Okay? And you graph this, and it actually looks like a parabola. Okay, however, you know it's not that simple, right? What's the problem here? There's a hole where? At x equals 1. Okay, there's a hole at x equals 1 that I know is going to be there. So let's sketch this with the hole. And really, if you think about what we're doing here, we are in part C finding the limit as x approaches 1. What do you get if you plug in 1? Undefined. Okay, it's 0 over 0. All right, so when we sketch this graph, it looks like this parabola, but at 1 we know there's a hole. Okay? So now that that's out of the way, how did we find the holes back in pre-calc honors?
You have to cross out top and bottom, and then we said we
Okay, if we cross out, we have to cancel out the thing that, yeah, we got to factor, all right? Now, for those of you who may be a little bit shaky on factoring, start practicing now, because it's not going away, okay? Start practicing your factoring. Here we have factoring on the top that we can do. What method would we use to factor in the numerator? The difference of cubes, okay? So, all right. So take a wild guess. What do you think is going to be in one of those parentheses?
X minus 1.
In x minus 1. We hope so, or else, you know, it's not going to really help us. And that actually is the case. Remember, difference of cubes, the first set of parentheses is a binomial, and each term is the cubic root, or the cube root of the two terms. So the cube root of x cubed is x, the cube root of negative 1 is negative 1, so x minus 1. Now, it is, you remember SOAP, same, opposite, always positive? That's how you can remember the signs. Same, opposite. So it was minus 1, so this one's going to be plus 1. And then always positive. It's always going to be plus, because that second set of parentheses will be a trinomial. Okay? So what goes in there? Well, the first and last terms are easy. It's just what's left after you take the cube root out of the two terms. So if you take the x out of an x cubed, you've got an x squared left. If you take a negative 1 out of the negative 1, you've got a positive 1 left. Okay, that's why it's always positive. But the middle term, how do we get the middle term? Yeah, you just multiply the two cube roots together. X times the 1 is just 1x, but then you make, or it's negative x, but then it's opposite sign, so you make it a plus x, and that's what makes all the inside stuff cancel out. Okay, that opposite sign. So here we're canceling things out, and we have x squared plus x plus 1. So now when we plug in 1, what is it getting us? 3. Okay, that hole is the point 1, 3. Okay, so guess what, guys? You guys have already done this. You just didn't realize that you were finding a limit. Okay, I just showed you the algebraic way of figuring out what this limit is. So the limit as x approaches 1 equals 3. Okay? So algebraically, remember I said you can factor and cancel stuff? In this case, that's the method we had to use. All right. Now this one worked out nicely. It doesn't always. So how do we use a table in order to figure out the value we're looking for? Okay. So let's look at how to find a table using the calculator. Because yeah, I know you could all do this by hand, but why? All right. You've done plenty of arithmetic up to this point in your lives, so we don't need to do a ton more. Okay. So I have this function already put in here. So you'll notice here it says table set right above the window button. We're going to hit table set, and we're going to set the independent variable to ask. This is really helpful because notice when we set up this table, we don't want to use just a consistent interval. I don't want to approach 1 by going 0.9, 0.8, 0.7, a tenth apart, because I may not see the pattern that's getting there. And I want to get really, really, really close to it. Okay? So by setting this on ask and setting up my table, you'll notice I start out 25/100ths away, then a tenth away, then 1/100th away, then 1,000th away. I'm getting exponentially closer to the value. That's going to let us see the pattern that we need to see much more easily. Okay? So I hit ask, and then you'll notice above graph it says table. So I'm going to hit second table, and it gives me a nice blank table. And what I can do at this point is I can simply type in 0.75 and hit enter. And you'll notice since I have my function stored as y1, it's giving me the value of the function when x is 0.75. Okay? You might say, well, wait, I thought the limit was 3. Well, it is, but notice what happens. Now when I punch in a 0.9, it's 2.71. And then when I do 0.99, it's 2.97. And when I do 0.999, it's 2.997. Okay? So I'm getting those values, 2.3125, 2.71, 2.9701, and 2.997. And by the way, what does it appear then that our left-hand limit is approaching? 3. And it looks like our left-hand limit is approaching 3. So now I've got to go from the other side, the 1.25. Okay, that's 3.8125. Okay, and then 1.1. I've got a 3.31. Yep.
Do we care about sig figs in this class?
We'll talk about that, but actually in AP Calculus we do everything 3 decimal places. Not sig figs, 3 decimals. So, and when in doubt, just give extra ones. They never take off for being more precise, but they will take off if you round too much.
Okay.
Okay? In that way, it's just like SL. Okay? 1.01, we got 3.0301. And if I put in 1.001, I've got 3.003. So now that we have all of our values, what does it appear that the right-hand limit is approaching? 3. Okay? So that confirms what we found algebraically, our limit is approaching 3. Okay? And just to use our notation, from this side, we're coming from the left, the limit of f of x as x approaches 1 from the left is 3. And coming from the right here, the limit as x approaches 1 from the positive side, from the right, of f of x is also 3. Okay? Does that make sense? All right. So, if f of x becomes close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. So that's what we just recognized there. And we actually already found this analytically. We found it analytically. When they say analytically, you could also say algebraically. That's what we did up here. When we reduced and did it. Analytically is going to give us an exact answer. Graphically and using a table, we can come up with a pretty good approximation. But remember, that's still just an approximation. I guess it's possible the limit could equal, 3.0005 or something like that. We won't know 100% for certain until we actually do it analytically. Okay? All right. Now, there are different cases when a limit will fail to exist. Okay? When a limit fails to exist, we can say D and E, the limit does not exist. Okay? Now there are 3 main cases where a limit does not exist. First of all, if the left-hand limit and the right-hand limit are not approaching the same value. Okay, a picture for this one is actually kind of useful. Remember I said we're using piecewise functions a lot in this class. This happens a lot in that case. You could have a function that's going like this, and then has some kind of a jump like that. The limit as we're approaching this value, whatever that is, would not exist, because from the left it's approaching this value up here, but from the right it's approaching this value down here. Okay, so that's possible, and in that case we would just say the limit does not exist. Another case is unbounded behavior. Okay, unbounded behavior. If you look at the graph of this function, it has a horizontal asymptote at 0, but it also has a vertical asymptote at 0, and it looks like this. Okay? Well, if you notice here, as x is approaching 0, from the left, what is our graph doing? Huh? Increasing how far? Infinitely, okay? And from the right-hand side, the value of y is increasing infinitely. All right? Now, is infinity a number? No. It's not a specific value. It's more of a concept. And this is where, depending on what website or what book you read, some people will say, well, the limit's approaching infinity. And that's true, okay? But we could say here that the limit does not exist because it's not approaching a specific value, all right? So we typically will say that the limit does not exist. I will tell you, even AP is a little inconsistent in this sometimes. Sometimes they'll, like on a multiple choice, they'll give you the option of, they won't give you both, but they might give you the option of positive infinity or they'll give you the option of does not exist. So just be aware that it can be expressed both ways. Another case here is this oscillating behavior. This is kind of a weird one. The key thing with oscillating behavior is that, what does it mean to oscillate?
Go back and forth.
Okay, it goes back and forth. The key here is that it's not just like a periodic function, all right? But it's something that as you're approaching it, it literally bounces back and forth faster and faster between two fixed values, okay? This graph, I'm trying to remember exactly what it looks like. It has some kind of a thing like this, but then as it approaches, it like just kind of goes nuts here in the middle, and then it starts and does something like that, okay? And even though I didn't draw it exactly right, this and this value are fixed values, and it just bounces back and forth between these two fixed values more and more and more as x approaches 0. That's oscillating behavior. It doesn't happen a whole lot, or at least not with stuff that we're going to be studying. You're not going to see this a lot, but just be aware that that is another way that you could get a limit that does not exist. Okay? All right. So, I want to take a minute here with this last one. Just to illustrate this last one, this oscillating behavior, I have a table set up here. Let's work through this. This will be a good trig review for us. Okay. Notice it's the limit as x approaches 0 of the sine of the reciprocal of x. Okay, 1 over x. So what am I taking the sine of when I plug in 2 over pi? Pi over 2. Okay, so it's 1 over 2 over pi is pi over 2. So what's the sine of pi over 2?
0. And the 1. Pi over 2. 1.
0 or 1?
Sine is cosine. 0. It's 1.
It's 1. All right. It's 1. Okay. How about what are we taking the sine of when x is 2 over 3 pi? All right. What's the sine of 3 pi over 2? Negative 1. Okay. Negative 1. How about 5 pi over 2? It's going to be 1. How about, yeah, you getting the pattern? Now notice I'm dividing by more and more and more, so that value of x is approaching 0, right? And I could even jump to the other side and be doing the same thing with the negative values of these. But notice it just keeps bouncing back and forth between 1 and negative 1. It's not actually approaching a specific value. It just keeps bouncing back and forth, back and forth, back and forth. So that's what we call the oscillating behavior. Limit does not exist. Okay? So, let's try this one, and we'll do it all 3 ways, okay? We'll graph it, we'll use the table, and then we'll try it analytically, okay? So I'm going to give you guys some time here to try this on your own. Let's see what you can come up with. All right, so you've had some time to work on this. Let's go ahead and take a quick look at it, and also algebraically just look at how you would solve it, or analytically we could say. So we've got the graph of it. It looks like this here. It looks like what parent function does it look like? Yeah, the square root or the radical function. It just has been shifted around a little bit or transformed a little bit. And we see the table over here. If we zoom in a bit, Okay, we have, you know, the negative 0.01, negative 0.001, negative 0.0001, and it just keeps adding more and more nines to it. All right. From the other side, we've got it 2.000499999, 2.00005, and on your calculators, this one actually you didn't even have enough digits, so it just rounded it to 2.0 on a lot of your calculators.
That's why.
And that's okay. That's just a rounding thing on the calculator. But that helps us really see as this gets more and more nines and this gets more and more zeros, you can see it honing in right there on the value 2. Okay? So we could then approximate that the limit is approximately 2. Now, we can prove that if we work through this analytically. Okay? If we work through it analytically, how would we got 0 over 0, so how do we cancel out that whole? Multiply by the conjugate. We need to rationalize. All right? So we've got the x over square root of x plus 1 minus 1. We're multiplying by the conjugate. Square root of x plus 1 plus 1. Now, guys, don't forget the whole point of doing this is because we want to cancel out the whole. The whole occurred when x was 0, so we should be able to cancel an x out of the top and bottom, because that's what would give us a whole at 0. All right? If that doesn't happen, then we can kind of just quit and say the limit doesn't exist. All right? Because there's no way to get rid of that. It's actually not a whole after all. So we work our way through this. We multiply it out. We have x times this over. What do you get when you multiply out the denominators? Just an x. Yeah, because it's x plus 1 minus 1, so those cancel out. All right? And now, just like we were hoping, we can cancel out the whole. And now we have the function without the whole, so we can plug in. Now we can evaluate when x is 0. 0 plus 1 square rooted plus 1. We've got our 2. So now we don't have to say approximately 2. We can say the limit equals 2. Okay? Does that make sense? Take some practice, take some getting used to, but it's not that bad of a process once you get the hang of it. Okay?